We already studied Bose-Einstein statistics, and it is used to study or analyze huge number of bosons. The property of bosons is any number of bosons can occupy any energy level. Suppose this is E1 energy level, this is E2 energy level. One boson can occupy E2 energy level, two boson can occupy this E2 energy level, 3, etc. But in the case of fermions, the property of fermions is they have half integral spins. So in the case of fermions, they obey Pauli's exclusion principle. Means no two identical fermions can never occupy a quantum state. That is, suppose this is the this is a state, this E1 energy level is a state, and we have a set of identical fermions, that is spin up fermions. And remember that the property of the spin means the spin is an intrinsic property of particles, and that property is derived from the relativistic quantum mechanics, and you don't have it in your UG syllabus. It is a type of angular momentum, intrinsic angular momentum. So something like the character, you have characters, that is the intrinsic property of you. So by Pauli's exclusion principle, no two identical fermions can never occupy a quantum state. That is, no two identical fermions. No, this is an identical fermion, this is an identical fermion, and this is not possible because by Pauli's exclusion principle, no two identical fermions can occupy a state. So only one identical fermion. From this set, only one identical fermion can occupy this state. Similarly, one identical fermion can occupy this state. But if we have another set of spin down particles like this, we can choose a spin up from this and spin down from this, like this. This is possible. This is possible because their quantum numbers are different. These two particles have one have plus half quantum number, these have minus half quantum number for their intrinsic spin angular momentum. So this is possible, but we have only the case of this, that is, our all fermions are identical and our all fermions are spin up. So only one fermion can occupy a quantum state. So this is E3 state, and one fermion can occupy this state, etc. And remember that we only put one fermions in these E1, E2, E3 energy levels. So the degeneracy of these energy levels is 1, that is G1 is equal to 1, G1, G2 is equal to 1, G3 is equal to 1. Because only one state in this one state have this energy value E1, only one state have the energy value E2, and only one state have the energy value E3. And suppose we have a fourth energy level E4, and three states have in this three states have this energy value E4. Three states have this energy value E4. One state, two state, three state. So by Pauli's exclusion principle, we can put one fermion in these three energy levels. So we can put one fermion here, one fermion here, one fermion here. So we can put maximum of 3 number of fermions in this E4 state. Why? Because the degeneracy of this E4 state is 3, and there are 3 independent states have the energy value E4. So let me ask you a question, that in how many ways I can put 2 particles into these 3 states? And it is actually a question from your +1 classes, that is, in how many ways 2 people can sit into 3 chairs. These 2 people is equivalent to these 2 particles, and these 3 chairs are equivalent to these 3 states of energy value E4. So it is actually, you know that from your +1 classes, it is actually 3p2. If need, you can put this man as Sumesh and this man as Ramesh, and in how many ways Sumesh and Ramesh can sit into these chairs? That is, you can number this chair 1, 2, 3. Sumesh come here, Ramesh come here, Sumesh come here, Ramesh come here, Ramesh come here, Sumesh come here. So I think it is, so this 3p2 is actually 3 3 into 2, that is in 6 ways. In 6 ways, Sumesh and Ramesh can sit into these chairs, and Sumesh and Ramesh are these 2 particles, and these 3 chairs are these 3 energy levels. So you say that we can arrange 3p2 ways. So in general case, we have n particles, we have a state, we have an energy level, suppose the energy level EI, this is an energy level EI, and this EI energy level have GI. GI is the degeneracy, means GI states have the energy value EI. GI states have the energy value EI. So this is the degeneracy. In here, in this case, have 3 states have the energy value E4, and this case GI states have the energy value EI. So we can say that GI P, and here 2 particles, and here suppose in this energy level we have Ni particles. So GIP Ni is the number of ways in which we can put Ni particles into these GI states. And the general expression, this is an easy expression, 3 into 2, that is an easy expression, but in general case you already know that GIP Ni is actually GI factorial over GI minus Ni factorial. And you can see that here, that is here in this case it is actually 3 factorial over 3 minus 2 factorial. 3 minus 2 is 3 minus 2 factorial, that is 3 minus 2 is what? 1 factorial. So this is equivalent to 3 factorial over 1 factorial, that is 3 factorial is what? 3 factorial is, this is equal to 3 factorial is 1 into 2 into 3, that is 6. So this is a more general expression, and these 2 expressions are equal. You can compute permutation in this way also. So the main point is the fermions are identical. We can't distinguish them into Sumesh and Ramesh. Look at here. Here the Sumesh and Ramesh are 2 different persons, and we can distinguish them into 2 persons because their properties, their characters, etc. are all different. But in the case of fermions, they are identical. We can distinguish it into 2 fermions like named Sumesh and Ramesh. And the basic reason for that is these their wave functions are overlapped, and you will study more about these identical particles in your PG, in your MSc syllabus. So our fermions are identical and their wave functions are overlapped. We can distinguish 2 fermions into Sumesh and Ramesh. So we can say that the number of ways we can put in this case, in the number of ways we can put 2 particles into these 3 states is actually 3p2, that we already studied, divided by 2 factorial. 2 factorial is arrangements that 2 particles can make themselves. So in general case we need GI, look here, GI P Ni divided by Ni factorial. That Ni factorial come from the number of ways in which that Ni particle can arrange themselves. So so we can write them it as GI factorial. Look here, GI factorial over GI minus Ni factorial divided by here and Ni factorial also, Ni factorial. So GI factorial over GI minus Ni factorial times Ni factorial is the number of ways in which we can put Ni identical fermions into GI states which have energy value EI. Now we have the number of ways in which Ni particles can be put into GI states which have energy eigenvalue EI is given by this expression. Imagine E1 energy level have G1 states and also N1 particles. So the number of ways in which
n1 particles can be put into G1 states is given by this expression. And also imagine E2 energy level have G2 states and also N2 particles. So the number of ways in which these N2 particles can be put into these G2 states is given by this expression. So the total number of ways in which the total number of particles can be put into all energy levels E1, E2, E3, etc up to EI, etc is given by the product of all these number of ways by the laws of probability theory. Like summation, we can also use a symbol of multiplication here, and this pi sub I corresponds to this product. So I can write this in this way, like I already said in Bose-Einstein statistics. Let me take a logarithm on both sides of this expression. On taking logarithm, this product symbol changes to the summation. Because why? Because log of a product A B equal to changes to summation log A plus log B. And also you know that logarithm of A over, I already said it in Bose-Einstein statistics, my lecture on Bose-Einstein statistics. You already know that log A over BC is equal to log A minus log B minus log C. So this whole thing becomes summation over I log gi factorial, that is equal to log A, and also minus log ni factorial minus log B minus log gi minus ni factorial. Very simple. You can see that there is a factorial symbol in this expression, so we need to use Stirling approximation. So Stirling approximation is basically an approximation for if this ni is very large, this Stirling approximation is valid. That is, you can evaluate log 50 factorial. Like you can see the log 50 factorial by using your computer, that 50 log 50 minus 50, that two things are approximately equal. So using Stirling approximation, you can write this log omega is equal to this gi this log gi factorial convert to, using Stirling approximation, gi log gi minus gi, and log ni factorial converts to ni log ni minus ni, and also this thing converts to gi minus ni log gi minus ni minus gi minus ni inside a bracket, and this minus symbol is here. Let me open up the brackets that give summation over I gi log gi minus gi and minus log ni plus ni. You can see here ni log ni plus ni, and also minus this minus comes inside, will give minus gi minus ni log gi minus ni, and also this minus and this minus give plus, so plus gi, and also this minus and this minus, this blue line connected minuses cancels and give plus, and this minus inside will give a minus. So in total we get a minus ni. You already know that the entropy S is given by kb log omega, and this omega is this actually, and this kb is the Boltzmann constant. And this if you have n number of particles, and if your omega is large, means you can put n number of particles, this n number of particles in lot of ways to the system. So entropy is basically the number of arrangements the system have, or simply the randomness. And also every system in the universe have the tendency to maximize its entropy. Means every system in the universe have the tendency to maximize its microstates, or every system in the universe have the tendency to maximize the number of arrangements the system have. Let me give you an example. If there is no teacher inside your class, then you simply not sit in the benches. You have the natural tendency to move inside the class, or you have the natural tendency to maximize your arrangements. The number of arrangements you have if you sit in your benches is very less arrangements. But if you move inside your classroom randomly, your arrangements is very large, and no one forces you to move inside the classroom if there is no teacher. And it's actually the natural tendency, the nature itself have the tendency to maximize the number of states, or to maximize the entropy. You already know that, and also I explained it in detail in our Bose-Einstein lecture, that suppose we have a function f of x is given by this graph, and the maximum of this function happen at this point, and this point you can easily see that change in this function f of x is equal to, or the differential of this f of x is equal to 0. But if you look at this region, you can see a change in this f of x, but at the point where the function is maximum, there is no change in this function. Differential of f of x is 0. So we can simply maximize the entropy using this trick. So we have the entropy kb log omega. We can maximize it by taking the differential delta s, delta kb log omega is equal to 0, and kb is a constant, so it cancels with 0, and we have delta log omega is equal to 0. So we need to take the differential of this equation. So if you look closer, you need to take the differential of gi, ni, log ni, etc. And in fact, there's delta gi is 0. Delta gi is 0. No change for the degeneracy of the state, because suppose if you have a state with the energy eigenvalue E1 and its degeneracy, imagine its degeneracy is 2, and this 2 is fixed, it have no change in fact. But in fact, the number of particles can be distributed into these states can be changed, because if suppose we have one fermion in this energy eigenvalue E1 and one fermion in this state, and also in this state, and also this is an energy level with the energy eigenvalue E2, and imagine there have 3 degeneracies, 1 degeneracy, 2 degeneracy, 3 degeneracy, and only one fermion is here. Maybe after some time one fermion from this state can be jumped to this state. It is possible, and fill here. So the ni, n1, n2, etc. can change. So there is a delta ni can exist, but delta gi is always 0, because the degeneracy, the number of states is fixed. It is 2 here, it is 3 here, it is fixed. On taking the differential, you can see that the differential of gi log gi minus gi is equal to 0. And the next thing is this ni log ni. So you minus ni log ni, you can take the differential of this thing by using the product rule of derivatives. So the differential of log ni is actually 1 by ni delta ni, because the derivative of log x is 1 by x. So due to the minus sign, we get minus delta ni here, we get minus delta ni over ni, and this first ni here, first into derivative of second, so this ni here, and the second into derivative of the first. Second means second function is log ni, so this log ni, so this log ni into derivative of the first. Derivative of the first is this ni, so minus log ni delta ni. And the next thing you need to take differential is this ni, that is actually delta ni. And the next function you need to take the differential is this minus gi minus ni, log gi minus ni. So differential of log gi minus ni is 1 by gi minus ni times the differential of gi using chain rule minus ni. And that is the differential of gi minus ni is differential of gi is 0 and differential of minus ni is that is you get look at this reading, you get 1 by gi minus ni times minus differential of this ni, and you can apply that result here using the you can compute the differential of this whole function using the product rule of derivatives. You get this is the first function, gi minus ni is the first function and log gi minus ni is the second function. So first function gi minus ni into differential of log gi minus ni, that is 1 by gi minus ni times minus delta ni. Look at here, minus delta ni, look at here, minus delta ni. So you get this, and second function is what, log gi minus ni, second into differential of the first one. Differential of the first one is gi minus ni, differential of gi minus ni is minus delta ni. So you get this, and the remaining thing you need to take the differential is this plus gi minus ni, and the differential of gi is 0 and the differential of this ni is minus delta ni. You can see that here is equal to 0 by this condition. You can see that this ni cancels to give minus delta ni here and a plus delta ni here. So in fact this minus delta ni and this plus delta ni cancelled, and you can see that this minus this gi minus ni and this gi minus ni cancels to 1, and this minus sign and this minus sign in total give plus delta ni here. So you will totally get plus delta ni here, and you can see that there is a minus delta ni here. So this plus delta ni, this plus delta ni and this minus delta ni cancelled, and also this minus sign and this minus sign combined to give a plus sign. So you in total you get minus log ni delta ni minus log ni delta ni plus log gi minus ni delta ni, look at here, is equal to 0, and their summation is here. So on putting the term with the minus sign as a second function, you get this minus log ni and log gi minus ni here, and also I take this delta ni common here. So very simple, is equal to 0. So this is in fact, you can see this as log a and this as log b. So you know that log a minus log b is equal to log a by b, but this is actually here it is written as log b by a. Why? Because if log a minus log b is equal to 0, that implies log a by b also 0, and also if log a minus log b is 0 implies what? Log a minus log b is 0 implies log, because due to the presence of that 0, log b minus log a is equal to 0. Log a minus log b is equal to 0 implies log b minus log a is equal to 0. That implies what? Log b by a is equal to 0. So if it is 0 in the RHS, look, you can write log a minus b as log b by a instead of log a by b. That is happened here. So now you have summation over I log ni over gi minus ni delta ni is equal to 0. In fact, you have some other conditions too, that is the total number of particles n is constant, and you can write the total number of particles as the number of particles in the energy level E1 plus number of particles in the energy level E2 plus number of particles in the energy level E3, etc. And if you take the differential of on both sides of this expression, you simply get differential of n is equal to summation over I delta ni is equal to 0. And also the total energy of the system is conservative, or total energy is conserved. So you can write the total energy E as a constant, and in fact the total energy, suppose you have n1 particles in this E1 energy level and n2 particles in this E2 energy level and n3 particles in this E3 energy level. So the total energy of these all particles is actually n1 into E1. So n1 particles have E1 energy. So n1 into E1 plus n2 into E2 plus n3 into E3 gives the total energy, and that total energy is conserved. So you can write total energy E as summation over I ni ei. This is actually, here we describe the only three energy levels, but in fact you have a lot of energy levels. So the total energy E is a constant. If you take the differential on both sides of this expression, you get differential of E is equal to summation over I ei delta ni, because ei has no change. Each energy level is fixed, it has no change. Each energy level is fixed, it has no change, but the ni can change because the number of particles n1 can get some energy and move to E2 energy level, and the particles in the E2 energy level can lose some energy and can move to E1 energy level, etc. So n1 can change. So you get this expression is equal to 0 because the differential of constant is 0. So in fact we have two more conditions, that is condition 3 and condition 4 for maximizing the entropy, this entropy kb log omega. That is in fact we have the maximum of this equation. The maximum of this equation should obey the condition 3 and the condition 4. So for that we use the trick of Lagrange multipliers. The trick of Lagrange multipliers is actually very simple. That is, if you have a function, if you have a function like this, and you already know that the maximum of function happened at this point, but if you have a condition like this, like a line here, then what is the maximum of this function f of x? This blue line is the function and this green line is the condition. So let me ask you, what is the maximum of this function f of x, that obey this condition green line? That is only this point, only this point. So this is actually a problem in mathematics. So we use the trick of Lagrange multipliers to find such values of the function that are constrained by some conditions. So using the trick of Lagrange multipliers, we can write equation 2 plus equation 3 and equation 4 are the conditions. So alpha times equation 3 plus beta times equation 4 is equal to 0, and this alpha and this beta are called the Lagrange multipliers, and they are just some parameters, and you can simply interpret this equation. That is, very simply you can interpret this. That is in fact this equation 2 is 0. So this 0 times, look at this equation 3. This equation 3 is also 0. So alpha times another 0, and also look at this equation 4, or this condition 4 is also 0. So beta times 0 is a big 0, because 0 plus 0 plus 0, alpha times 0 plus beta times 0 is equal to a big 0. So that is actually returned, actually wrote here. Equation 2 plus alpha times equation 3 plus beta times equation 4 is equal to 0. So put in equation 2, equation alpha times equation 3, beta times equation 4, you simply get this equation. That is, equation 2 is here. Look at here. Log gi, log ni over gi minus ni is here, and this alpha is delta ni comes in common, so alpha delta ni comes in common, so alpha is here, and beta times ei here, and this delta ni comes in common. And in general, this delta ni may or may not be equal to 0. So to obey this condition, we must have log ni gi minus ni plus alpha plus, that is, this thing should be equal to 0. Alpha plus beta ei is equal to 0. So from this equation you can simply write log ni over gi minus ni is equal to this alpha plus beta ei comes to the RHS. You get minus alpha plus beta ei. And if you take the exponential on both sides, you already know that logarithm cancels with the exponential. So you get ni over gi minus ni is equal to e to the power alpha plus beta times ei. And this is actually equal to 1 over e to the power alpha plus beta ei. That is x raised to minus 1 equal to 1 by x. So you get this equation. From this expression, we can simply write an equation for this e to the power alpha plus beta ei. That is e to the alpha plus beta. This thing come to the numerator. We get this gi minus ni come to the numerator, ni come to the denominator. And doing that, we get gi minus ni over ni. And if I divide this gi minus ni with this ni, we get gi over ni minus ni over ni is 1. We get this. And if I put this 1 to this LHS, I get 1 plus e to the power alpha plus beta ei is equal to gi over ni. And this equation you can simply write this ni by taking this ni to the numerator of the RHS. You get ni is equal to gi over 1 plus this thing come downward. I get gi over 1 plus e to the power alpha plus beta ei. This is the Fermi-Dirac distribution law. If you are asked to derive Fermi-Dirac distribution law in your exams, just derive up to this point. And also we can find alpha and beta like in our Maxwell-Boltzmann statistics, and it does not include in your UG syllabus. So if you wish to study it by yourself, just contact me. I will give you enough information to derive this alpha and this beta. If you so we can find this parameters alpha and beta as alpha is equal to minus mu over kBt and beta is equal to 1 over kBt, and this mu is called the chemical potential. So on putting this alpha and beta in this expression, we get ni is equal to gi over 1 plus e to the power ei minus mu over kBt. We can set this parameter mu is equal to Ef, and Ef is called the Fermi energy. And you get ni. I just take this gi to the denominator. You get ni over gi is equal to 1 over 1 plus E minus Ef over kBt. Just I said mu is equal to Ef, and I write this thing as a function of E, f of E. And this Ef is the value of energy for which the value of f of E is equal to 1 by 2. And you can apply this result. You need to apply this result for deriving the free electron theory of metals. And the free electron theory of metals is one of the main application for Fermi-Dirac distribution law.